again fast
Yeah, so there is no reason to use some small edge twice because
there is no reason and there is no possibility. In fact, at least if you are not using external edges twice, there is no way to use internal edges twice. So if your external edges are used once, at most once, then the same holds for internal edges.
So it seems that it's now a very rare occasion when you explain in detail something which is really understandable.
Oh, that's great. But that's not all.
I have.
Oh, great. So this also implies that if you are explicitly given a set of forks, that you are given a fork environment, then you can decide in linear time. Of course, if you already believe that Goldberg and Karzanov are capable of doing that for directed graphs, for bidirected graphs, then you are also capable of solving the very same problem for the case of a general fork environment. Well, next I'm going to talk about certain special cases. In fact, one special case which seems to be important because well, here the size of the input and the complexity of your algorithm is linear in terms of the total size of a graph plus the additional size of a fork framework. And of course there is no easy way to get rid of this fact because fork framework can be rather large. Its size is proportional to the sum of squares of degrees because you have to specify which edges form forks. And but for some special cases of fork environments, the information can be stored in a much more compact way. Let me introduce you the notion of an anti-transitive fork environment, which may sound strange. Anti-transitive. A fork environment is called anti-transitive if for each triple of distinct edges which are incident to some node, the following holds. If E1 and E2 is a fork, then E1 and E3 is a fork. Or E2 and E3 is a fork. Sounds strange, doesn't it? So if you have a fork, these two edges form a fork, and you have any third edge, then either the first edge plus third edge is a fork, or second edge plus third edge is a fork.
So for example, for this male-female cable, it's true.
It's true,
For directed graph.
Well, it's true. It's also true when you have an undirected graph, that is, all possible pairs form forks.
Is that OR exclusive?
No, it's ordinary OR. You can have both of these statements true. And does anybody understand why we call it anti-transitive?
No.
Oh, that's very nice. It's not nice that you don't understand.
This relation to be a fork is symmetric. So we can write also E sub 3 and E sub 2. Then it's clear, because if we take the contraposition of this, we will obtain, if these guys are not forks both, then that is not fork either.
So if you have a relation not being a fork,
it is transitive.
It is transitive.
And symmetric.
And of course symmetric because the original relation is transitive. So the negation of relation to be a fork is transitive.
So the more politically correct name will be cotransitive. I remember that a friend of mine in his thesis has a Chinese remainder lemma and some other lemma which is called anti-Chinese remainder lemma.
Now, that wasn't political. I believe that transitivity is not such a term which can
but you never know.
hurt anybody. Well, if someone, someone considers himself transitive, it's not against transitive people.
Maxim, and also it is reflexive, I understand.
It is reflexive because we do not allow E1 to be equal to E2.
Yeah. So it's equivalence relation.
Yes. So what you want to say is probably it's a way to if it's antitransitive, you can describe the relation in much shorter, listing the equivalence classes of the complement.
Yeah. If we have an antitransitive Fock environment, if you remember, I was talking about graphs GV attached to every of possible nodes. And if your Fock environment is antitransitive, then its negated relation is equivalence because it is reflexive, it is transitive, and it is symmetric. So, what are the graphs GV in case of antitransitive Fock environment? How do they look like? Multipartite graphs.
Multipartite graph with all
because you have certain equivalence classes taken with respect to the negated equivalence, with the negated relation.
Yeah, so just the end of cables have colors. And the only rule is you cannot connect the cables of the same color, but you can do whatever you want with a different color.
Exactly. Yeah. So in case your Fock environment is antitransitive, this means that these graphs are multipartite. In particular, they can be one-partite. They can consist of one part, which means that there are no forks at all. They can consist of two parts, which means that you have male and female endpoints. And you can have each node in its separate part, which means that the graph is complete. And this corresponds to the case of undirected graphs, where you can consider arbitrary forks. So this way, we can store our information about Fock environment in a much shorter form. We can do the following. For each endpoint, we mark it with certain color, some integer number. And the only requirement is that as you go along your walk, you should be changing colors at each inner node. So the description is much shorter. And what about the reduction? In fact, it turns out that we can present a different structure to be embedded instead of GV, and that structure is much smaller.
Reduction of what to what?
We were talking about the reduction from Fock environment to bidirected graphs. And that reduction, the size of the output of that reduction was proportional to the size of the Fock environment. And now our Fock environment can be expressed in much shorter way.
So what you do is to present a more effective reduction, for antitransitive environment.
If the environment is antitransitive, we can do the following. Instead of embedding GV, well, suppose that GV is three-partite graph. It has three parts. So you have some part here, and some part here. What we were doing originally, we were connecting each pair of edges each pair of nodes belonging to different color classes with an auxiliary edge. Now let's do a different thing. Oh, I'm sorry. That should be done this way. Now let's first collect these ends belonging to the same class. And direct them, I don't know, this way, for example. And then add one more central node. And connect it in this way. And add the loop here, which leaves its only endpoint twice. So it's clear that the size of this construction is linear. The size of the graph is linear in terms of the number of edges incident to the node V. And it's also clear that it serves the same function, merely. You can connect two nodes by directed walk, if and only if they belong to different color classes. So, if you have two nodes, for example, here and here, yes, you can connect them. You should go to the central node, then along this loop, and then go here.
If you want to do it only once.
Yeah.
If you have to make many connections, then you cannot use this. But so.
Yes.
But we are not interested in this.
Yes, we are not interested. But if you want to use it many times, you can. Well, it turns out to be very simple to prove that you shouldn't be using any node more than twice, and hence you can add the second loop, and this way you can also include not simple paths.
We assume now that we are searching for reachability.
Reachability, yes, exactly.
By a node.
By an edge simple.
Edge simple path. So we indeed need this two copies of this.
Yeah.
Just maybe.
Yeah, that's right. Let's draw the second copy, because yes, it's possible that you pass through this node twice, and this way you should need to use the second copy of this loop.
Why don't we need it?
Another copy to the center.
Sorry?
Why don't we need it to use it 3 times?
3 times. Well, because of the following. Suppose that you have passed through certain node once.
Mm-hmm.
So you have certain colors, for example, 1 and 2.
Mm-hmm.
And then you are going through it second time, for the second time. And what you have here is, I believe, well, you have, as long as you cannot make a shortcut here, you cannot drop this cyclic part.
That outer is 1, 2, yeah.
Yes, 1. And the color here is not necessarily 2, I believe.
Yeah.
It might be 3 or something like this. Ah, well, no, I'm not right. You can use this central node not 2 times, but many times. But this number of times doesn't exceed the number of color classes. So we add as many loops here, as many colors we have here.
Not the pairs of colors.
Not the pairs. Not just.
Also, Alyosha points that you need also not only the loop used twice, but the middle.
Center and matching.
Okay, so we have to replicate certain edges here, namely
but it's
the
still
loops
linear in the number.
and these auxiliary edges, and the number of replications is just the number of color classes, so it's still linear. Still linear. Thank you. So, well,
what is the proof of that?
the proof of that, okay. So suppose let's prove that we don't need to pass through any node more times than the number of color classes at this node. Just by simple reasoning.
If we use the same color twice, we can just.
If you cannot make shortcuts, then this means that each time you are entering this node, you are using some color, and when you are leaving this node, you are using the very same color 1. So when you are entering 3rd time, you should have 4 and again 1, and next time 5 and again 1, and so you can run out of colors, just because it is so. Okay. But by the way, if we do not replicate this structure here, we can also look for paths which are not simple. It's very important because of the following. I'm not aware if there is any way we can solve a not simple reachability problem in a general fork environment. So if your fork environment is anti-transitive, you can use this reduction. You can use only a single copy of this loop, and automatically what you get is a not simple version of reachability. But if you have a general fork environment, it's not clear if we can do it at all. So perhaps it's an NP-hard problem, I don't know. Well, Do I have 5 minutes more? Yeah?
Yeah, but also since we don't know what happens with the coffee, so probably you can safely continue.
Oh, that's great.
No, Sasha.
That's great.
No, coffee is there.
Coffee breaks will be in room 404. Right, already budgeted.
Well, it's nice to know that we have an algorithm which can check something in linear time, but it's also nice to know that we have it's also nice to know that we have certain structural results which describe the reachability. Well, if you have a certain node B reachable from certain node A, then to prove this you can just present your path. Just give it explicitly. But what can be the proof? What can be a proof that no such path exists? Some sort of a certificate which can be checked in a very simple way and which can ensure that no such path in fact exists. And there is such a certificate known for the case of bidirected graphs. And I'm not sure if I will be on time if I start talking about its fork environmental version. But let me explain it for bidirected graph. It's rather simple, in fact. First, let us focus on a case where we're looking for a path, a very strange thing. We're looking for a path which connects a node to itself. It's called NS path. There is no requirement about the directions of the first stage and the last stage. And it also can be shown in a very easy way that we can reduce the general reachability when we're looking for a path from A to B to this case by adding some extra node S and augmenting our graph with a pair of edges. Let me just skip these details for sake of completeness. And
so you want to describe some kind of obstacle for the existence of this path. What is this obstacle?
What is an obstacle? First, let us know that there is a natural equivalence on the class of bidirected graphs. That is, if you have a certain node, you have edges entering it and edges leaving it. You can easily flip directions. You can say that, oh no, these edges are not entering, they are in fact leaving. And vice versa. That's because the actual name of the direction isn't important. We only need that the directions are different. At each node the directions are different. And this equivalence allows us to say the following thing, that the obstacle, a possible obstacle for an existence of such a path is the following. Suppose that your graph can be flipped into, that is, there is a graph equivalent to your original one, and which can be partitioned as follows. You have certain large part S capital, where your S is. You have some part called M. It's a trash, in fact. And you have certain parts which are called B1, B2, and BK here. And the structure of edges is the following. Well, we may assume that all edges leave S because we are not worried about the directions of edges at S. We are looking for an S path. And we allow the following types of edges here. Only edges that leave one of its point and enter another one, and edges that enter both ends. These two types are allowed here. Then
we cannot connect anything inside S because there is
we cannot connect.
The thing which is needed is missing.
Yeah, the only interesting thing is missing. In fact, we cannot have an edge which leaves both endpoints. If we have such an edge, then it is possible to make a connection. So there are no restrictions on what edges are allowed here, here, and here inside B1, B2, and there. But there are restrictions on what types of edges are allowed to connect these parts. Well, the requirement here is that every edge which connects S and M enters S. So in fact, this means that you cannot reach M at all. M is the trash part. This is an unreachable part of your graph. You can start from S, but there is no way you can traverse this edge at all. And what about B1, B2, and BK? These are interesting parts. The following property should hold. For each such part, there is a unique edge which leaves S and goes to B1, B2, BK. And an arbitrary number of other edges are possible between S and BKs. But all these edges enter S, not leave. So a unique edge goes from, connects S and B and leaves S. And all other edges, they go back. So why can't we have an S path here? Well, because if we start from S, then we traverse some part of S capital, we cannot reach M at all. Yes, we can go to B, but S, the only possibility for us to go to B is to use this unique edge. And once this unique edge is used, we cannot use it again. So what we can do is we can return back to S. But then the direction of this edge will be again forward. So if you...
What is about the edge between BK?
There are no edges between
just
B's and no edges between B's and M. Mm-hmm. So these are the...
So now this is the complete description of the obstacle.
Yes.
So even if we don't know that the class of the problem is in P, we still can see why it's, not why, but how it's in a coin.
Yeah, it's...
What is the obstacle for to vertices being
But to see this, we need a proof that it's...
Yeah, of course.
That this obstacle exists, yes.
Yeah, but at least it's a kind of picture of what is the obstacle.
It's crucial that you have a single edge going to B, because if you
have two of them,
if you have two of them, then it's...
Or if you have edges connecting B and B.
If B and B, it's again bad, because you can then B then go to B, and then use this edge and get an S path, like this one, for example. You can go here, then here, 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 then here, then here, and here. So if you have edges going between B's, it's not an obstacle. Well, it is proved that it's a complete description of reachability. I mean, reachability of S from itself.
So it's a kind of linear programming duality, or what?
It can be extracted from linear programming duality, but there are simple combinatorial proofs, which are, in fact, the proofs of correctness of certain algorithm, which looks for a path, and if it doesn't find a path, it finds this kind of obstacle. And it turns out that there is a way we can extend general fork environments. I mean, we can extend this notion of an obstacle to a general fork environment.
And this is the main achievement.
It's not an achievement. It's a very simple thing, I believe. Yeah. And it's as follows. It's very simple. Just look at the very same picture. Suppose that you don't have a bidirected graph, but instead you have a certain fork environment. Let's do the following thing. Let us turn our graph G into a bidirected graph. In some way, that is, let us assign directions to edges with only one requirement. And the requirement is the following. If you have a node and if you have two edges entering it, then this pair is not a fork. A very strange, at a first glance, requirement, but not a fork. So we consider all possible ways to assign directions, with only one requirement, that if two edges enter something, that this pair is not a fork. And it